This generated video shows a massive tower of metallic blocks, wobbling and eventually collapsing under its own structural weight. It illustrates a core tension in scaling autonomous agents. Adding new capabilities increases structural fragility. To get a large language model to perform continuous functions, engineers have had to stitch together a web of third-party API wrappers and manually configured database synchronizations. This fragmented architecture leads to two severe operational roadblocks: runaway API costs and rapid context degradation the longer an agent runs. This animated diagram shows how Openclaw 4.5 targets that exact problem. On the left is the standard pipeline, a fragmented network of disconnected nodes orbiting an agent. On the right, those nodes smoothly collapse and integrate tightly inside a single central core orchestrator. Openclaw 4.5 operates as an integrated multimodal engine, centralizing tools that previously required separate API management. We will break down exactly how this updated architecture works, starting with autonomous memory systems, moving into cost-saving caching infrastructure, and finishing with native media generation. Eliminating the latency caused by external middleware hops is necessary for deploying production-grade 24/7 autonomous agents. The critical flaw of any long-running AI agent is context degradation. Over time, the agent loses statefulness, forgetting previous interactions and executing redundant tasks. The standard developer workaround requires engineers to manually parse massive operational logs to decide which specific pieces of information need to be saved. Manually updating these long-term context files creates a hard bottleneck. It forces automation architects to spend hours maintaining basic memory hygiene instead of building new capabilities. Openclaw 4.5 introduces an architecture called memory dreaming. This is a native automated replacement for manual context hygiene. Rather than acting as simple long-term storage, this is a self-regulating context architecture designed specifically to keep agents coherent entirely unsupervised. This diagram illustrates the first phase, known as light dreaming. A horizontal scanning line quickly sweeps across a short-term context log filled with data blocks. This represents a rapid, low-compute pass to flag notable recent activity. The system then enters deep dreaming. The agent cross-references these flagged blocks to identify broader structural patterns across the entire data stack. Finally, the system executes the REM sleep phase. It makes active decisions about which network data gets committed to long-term memory, while the unhighlighted blocks dissolve into an archive folder. This consolidated, high-value data is permanently written into a persistent file labeled dreams.md. Engineers are not locked into a black box. The system includes configurable aging controls, allowing developers to adjust exactly how aggressively the agent promotes or discards these memories over time. There is also a dedicated Dreams UI tool that allows you to inspect the exact logic path the agent used when choosing to promote specific memories. By translating a biological sleep cycle into a digital architecture, Openclaw creates a zero-touch solution for maintaining persistent statefulness across continuous agent runs. Maintaining statefulness solves one problem, but heavy, daily cron job pipelines introduce another: massive API burn rates. Prompt caching is often touted as the solution, but in legacy setups, it frequently fails. Variable payload structures and transport fallbacks constantly break the cache between runs, forcing the system to reprocess identical data. This diagram shows Openclaw 4.5's structural fix: deterministic MCP tool ordering. On the top, a sequence with scrambled shapes hits a red cache miss node, burning API credits. On the bottom, a sequence with strictly ordered identical shapes hits a green cache hit node, preserving credits. By forcing a standardized, repeatable payload sequence, the architecture guarantees high rates of cache reuse. To track this, developers can run a new diagnostic command, Openclaw status, with the verbose flag. This verbose terminal flag outputs immediate, real-world diagnostics on your actual cache reuse rates directly in the console. Crucially, these caching improvements are maintained even when the system encounters transport fallbacks. Deterministic ordering provides a measurable mathematical reduction in monthly operating costs. To support these optimizations, the platform has expanded its out-of-the-box provider endpoints, adding native support for Quinn, Fireworks AI, StepFun, and Llama Web Search. For enterprise users, there is a new AWS integration via Bedrock Mantle. This includes an auto-discovery mechanism designed specifically to route embedding models like Titan and Cohere. Administrators also gain a new privacy feature, per-channel context visibility settings. This setting gives developers granular control over exactly what specific data streams an agent can ingest, which is critical when deploying bots in shared multi-user workspaces. Coupled with the deprecation of the legacy Claude CLI and the native embedding of the ACPX runtime, these updates standardize the platform for enterprise deployment. This generated video shows a mechanical arm rapidly assembling a glowing, complex geometric core. It represents the final architectural pillar of this update, multimodal execution. In legacy systems, an agent must stop its execution loop and wait for an external API wrapper to return an image. Openclaw 4.5 connects to media generators natively. The platform now integrates directly with video models, including X's Grok, Alibaba's Wand, and Runway Gen. It also bundles audio generation natively, supporting both Google Lyra and Miniax. This diagram shows the core logic making this possible: async task tracking. We see a primary execution thread represented by a solid line. A node splits off this main line, dropping onto a parallel progress bar labeled Media Task. The agent offloads the compute-heavy generation to this parallel process and immediately resumes its primary execution loop, continuing to work without waiting. The platform monitors the job in the background. Once finished, it automatically syncs the completed media package back to the agent, completely eliminating the need for manual polling scripts. For local-first developers, the platform directly bundles Comfy UI workflows into this exact same asynchronous interface. Asynchronous task tracking alters the underlying behavior of the agent. It allows the model to act as a true concurrent system, synthesizing its own media without stalling its primary directive. To see how these systems interact, we can walk through a complete 24-hour execution cycle of an Openclaw 4.5 agent. Step 1. The agent triggers its daily cron job. Because it uses deterministic ordering, the payload hits the prompt cache perfectly, immediately reducing the API cost for the run. Step 2. The agent asynchronously triggers a video generation task. It then moves directly onto its secondary tasks, continuing to work without blocking. This circular state machine diagram tracks the full sequence. Step 3. The cycle concludes as the agent enters its REM sleep phase. During this final phase, the agent automatically cleans its context window and updates the dreams.md file, archiving the day's work and readying itself for the next run. As these technical capabilities have expanded, so has the platform's accessibility, rolling out 12 new languages natively integrated into the control UI. By engineering statefulness, cost efficiency, and parallel multimodality directly into the core loop, Openclaw 4.5 provides the foundational infrastructure required to run completely unsupervised AI pipelines.